So in this video I want to talk a little bit about Patel's rule, which is another application now that we know how to take derivatives. At the beginning of the Calc 1 class we spent a lot of time taking limits, and there's definitely some limits that were more challenging to evaluate, and we used algebra techniques to evaluate them. Sometimes we used what I call the near side method, where we just get really close to the graph and kind of look what's happening on both sides of the thing that x is approaching. Well, so this is just another technique for evaluating limits. It's called Patel's rule. So the idea is that if you're trying to evaluate a limit, usually the first thing you do is plug in the value that x is approaching, not because that's what the limit tells us to do, but because if it's a continuous function, then the limit will be equal to the functional value. So we just plug it in to see if it works. If we plug in the number that x is approaching and it gives us a number other than, well, if it gives us a number, constant, then that is the thing that it's approaching. So, but there's plenty of limits where we plug in the value that x is approaching and it doesn't give us anything. So like, for example, this one we're looking at right now, the limit as x approaches 0 of x squared minus 4 over x minus 2. Whoops, that one does give us something. I wrote that wrong. I meant for this to be 2. In this case, when we plug in 2, we get 0 on the bottom, which we all know is gives us an undefined value. So in the past, we handled this by taking the limit as x approaches 2 and factoring the top and bottom, x minus 2, x plus 2. And we noticed that we could cancel the x minus 2 out. Because as x approaches 2, this would not be 0 over 0. It would be some other number, which equals 1. So we end up with the limit as x approaches 2 of x plus 2. And now when we go to evaluate that, we can clearly see that as x approaches 2, this value approaches 4. So that's a way to do it algebraically. But let's say we didn't see the factoring or whatever, or just for argument's sake, we're going to do it another way, or just for learning's sake. So the other option would be to use Patel's rule. And the idea of Patel's rule is it applies anytime you have what is called the indeterminate form. The indeterminate form is, the two main indeterminate forms are 0 over 0 or infinity over infinity. And the infinity could be positive or negative. It doesn't matter. Okay? So if you plug in the value that x is approaching and you get 0 over 0 or infinity over infinity, then you can use Patel's rule. Now there's other indeterminate forms, like there's 0 times infinity. Let's see, what are some of the other ones? There's infinity minus infinity. There's 1 to the infinity, and there's 0 to the 0 power, and infinity to the 0 power. So anyway, there's a bunch of them. We're going to focus mainly in this class on these two because that's the ones that show up the most. But just be aware that there's other indeterminate forms. Okay? And they're called indeterminate forms because basically we can't really determine what's happening. If I end up with 0 over 0, just like we did here, it's possible that there's something going on that we just can't recognize by plugging the number in. So, so anytime we get the indeterminate form, Patel's rule applies. Now, Patel's rule says that if you have a limit of something like this, then, and you end up plugging in a, if f of a over g of a equals 0 over 0 or infinity over infinity, then you can apply Patel's rule. And what Patel's rule says, that this is equal to this. So in other words, I can take the derivative of the top and the derivative of the bottom and then reevaluate the limit. Now notice this is not taking the derivative of the whole function, because in that case we'd have to use the quotient rule. It's just taking the derivative of the top of the fraction, taking the derivative of the bottom of the fraction, writing it again as a fraction, and then taking the limit of that. Okay? So that's the idea of Laplace. And then you would just evaluate this new limit, because we're saying that whatever this limit is, it's going to be equal to that limit. We're not saying these are the same thing. They're only equal because of Patel's rule, because we got an indeterminate form on this first one. Okay? So that's the idea of Patel's rule. So we're going to apply that to a couple of examples here. So in this case, when I plug in 2, I get 0 over 0, which is one of the indeterminate forms. So that means by Patel's rule, and it's good to write that so that you know that so that whoever's viewing what you're doing is not just thinking you're changing the limit. I'm going to say this is equal to x as x approaches 2 of the derivative of that, which of course would be 2x, derivative of that, which would just be 1. So by Patel's rule, we're saying that this limit is equal to that limit, and that limit is clearly equal to 4, which of course is the same thing we got last time when we were doing algebra, right? So therefore, because of Patel's rule, we can say that this one is also equal to 4. So here's another one that I think we had trouble with back in the day because there was no algebra technique for dealing with it, and so we actually, I think, there was a web-work problem, I think, that dealt with this, and so you had to use the nearsighted approach, just look at the graph. So, but notice when we plug in 0 for sine x, we get 0. When we plug in 0 for x, we get 0. So this is the indeterminate form. So we're going to use Patel's rule. So by Lehop, I'm just going to write that so people know what I'm doing. This thing is equal to the derivative of sine x, which would be cosine x, over derivative of x, which would be 1. So then we're just saying, as x approaches 0, cosine approaches 1, right? So that means that this is also equal to 1. Okay, and let me do one more example. Here's one where x approaches infinity. When I plug it in infinity here, as x gets bigger, natural log just gets bigger, because remember the natural log graph looks like this. So as we go out to the right, it just gets bigger and bigger. So I'm going to have infinity on top. And as we plug in bigger and bigger values for x, x squared becomes infinitely large. So we end up with the indeterminate form of infinity divided by infinity. So we can use Patel's rule. So by Lehop, we know that that is equal to the derivative of this, which would be derivative of 3 is 0. The derivative of ln x is 1 over x. The derivative of x squared is 2x, and the derivative of 7 is 0. So we end up with 1 over x over 2x. Of course, if we do a little bit of algebra here, we get 1 over x times 1 over 2x, because we're dividing by a fraction, so we multiply the reciprocal, and we end up with the limit as x approaches infinity of 1 over 2x squared. And we know that as for the fraction where the top is set and the bottom is growing, that overall fraction is going to go to 0, so we know the limit is 0. So therefore, once again, we said because we got the indeterminate form up here, by Patel's rule, we said that this limit is equal to that limit, and then we just evaluated this limit and got 0, so therefore this limit also equals 0. Okay, so that's a quick little introduction to Patel's rule. There's a worksheet in the Canvas that will give you a bunch of practice with that, and have fun.